Good morning, everybody. Sorry I'm not there today, but I'll make a quick video here for the notes for you to go through some stuff. It won't take very long, and as long as you finish it in class, that means you won't have any homework tonight. So what I would suggest is hopefully you'll get your quizzes back in class, and once you're done watching this video, go ahead and, like on a separate sheet of paper, make some corrections for your quiz to help you prepare. We're going to do a quiz retake on Tuesday when we review for our test, which is Wednesday. So let's get right into it. So today's notes are all about modeling quadratics. So up to this point, we have worked with standard form, we've worked with intercept form, and we have worked with vertex form, which is what we just finished up with the transformations. So now we're going to look at how you can model those in some word problems. And the most significant word problem that you'll get when in terms of quadratics is vertical motion. And what we mean by that is like when you throw a baseball, or when a cannon is propelled out of a cannonball is propelled out of a cannon. Okay, there is actually a formula written down that will tell you the height of the object after a certain amount of time. And so in this formula, you have time, you have the velocity, which is the speed of the cannonball or the baseball, and then you have s, which is the initial height. So again, this is a very recognizable formula that is used for quadratics that talks about vertical motion. All right, and so you're going to see in this first example, for instance, you'll typically plug in for the velocity and the initial height, and then it'll give you a height after you say, okay, well, it's been in the air for 2 seconds. How high off the ground is it, right? And you can think of that even with the baseball. When you throw it, let's say you throw it 300 yards, but halfway through you want to figure out how high up that baseball went. Well, if you know where you threw it from, and if you know how long it was in the air at that point, and if you know how fast you threw it, then you'll know exactly how high off the ground it is. So in example 1, it says a ball is launched into the air such that the height of the ball can be found using the formula negative 16t squared plus 48t plus 100. How do we figure out at what height the ball was launched from? And as you'll see, okay, up here it says the initial height of the object is s, which is the constant at the end. So we call this the c term. Right? If you remember, okay, we listed out standard form would be ax squared plus bx plus c. So c is the c term, and that would be the 100. Okay, so what part of the parabola is this if we're looking at the graph? Well, if you look at the graph over here, you can see that it touches 100 on the y-axis. So in terms of the graph, this would be the y-intercept. Okay, so the y-intercept tells us exactly where the ball is launched from. So think about like a baseball again. If I launch a baseball or throw a baseball, it doesn't start from 0 feet. If I'm 6 feet tall, it's probably going to start from about 6 feet or maybe a little bit above if I throw it from above my head. Okay, so how can we figure out the maximum height of the ball? Well, the maximum height, of course, is at, since it's the maximum, it's at the tallest point, right, of the graph. And what part of the parabola what do we call the tallest point? We would call that the vertex. Okay. I know, bad handwriting here, and I apologize. But yeah, what part of the parabola is it? It's called the vertex, right? So you can find the initial value or the starting height by looking at the y-intercept, and then you can find the tallest point by looking at the vertex. And you would say, okay, what's the y value right there? So in this example, it looks like the y value would be around 135, 136, something like that would be your maximum height of the ball, so 136 feet. And then how can we determine when the ball hit the ground? Well, if we assume that the ground is at 0, then we would say when the parabola hits 0, right? And so what part of the parabola is that? Well, when the parabola hits 0, so the ball goes up in the air and then it comes back down, that would be over here, which is what we call the x-intercept. So when modeling, you're really looking for the x and y intercepts. You're looking for the vertex, right? And that tells you a lot of information about projectiles. Okay, so let's take a look at a couple examples here. We're going to use Desmos to graph it, and then we'll answer the questions that go along with it. So example 2 says a startled cat jumps straight into the air with an initial velocity of 32 feet per second, and the height formula for the cat would be h of t equals negative 16t squared plus 32t. So let's go ahead and plug that in, but instead of using t, we're just going to use x. So negative 16x squared plus 32x, right? And that should tell you enough information. See if I can zoom out here. Okay. So it asks, when graphing this quadratic in Desmos, how long before the cat hits the ground? So if this is a function of height, or a function of time, but gives you the height, so then all we need to know is that x, in this case, is our time. So we look and say how long until the cat hits the ground. We know that that's going to be when it touches, when y equals 0. So that's your time. And in this case, if you click that x-intercept, it's going to be 2 seconds. Okay. How high does the cat jump? Well, that's pretty easy. You go to the vertex, and what's the total feet? 16 feet. And at what time does the cat reach that height? Well, as you can see in that ordered pair, 1, 16, it would be after 1 second. Sorry, it felt like I was going to sneeze. Oh, turns out I did. I'm sorry. Excuse me. Okay, Fortnite has made another update. It's kind of an older game, but that's all right. Another update to their game and have added cannons to the top of buildings and tilted towers. You land on the top of the building 48 feet in the air and launch a cannonball at a velocity of 64 feet per second. Excuse me. We're having all kinds of difficulty here. The height of the cannonball is given by the quadratic function, negative 16t squared plus 64t plus 48. Graph this quadratic in Desmos and answer these questions. How long before the cannonball hits the ground? So let's go ahead and graph this one. And as you'll notice, they all start with negative 16t squared. What changes is your starting height and your velocity. So this one's got 64 velocity and starts at 48 feet. So how long before it hits the ground? Ooh, we're going to have to zoom out and find this one. It's going to take about 4.6 seconds. Okay, and always pay attention to what they want you to round to. In this case, it doesn't say anything, so we're just going to go with the nearest tenth. What is the maximum height of the cannonball? That's pretty easy, 112 feet. And at what time does it reach that height? Well, that would be after 2 seconds. But then it asks, when is the cannonball 100 feet above the ground? Well, you can see on the graph here that it reaches it twice, like right about here and right about here, because it reaches the 100 feet on the way up and on the way down. So in Desmos, the easiest way to do this is to recognize that it's asking for a y value. So we're going to plug in y equals 100. That's going to draw a graph, and it gives us those exact measurements. When does it hit 100 feet in the air? Well, it reaches it at 1.134 seconds and 2.866 seconds. Okay, so it actually reaches it twice, once on the way up and once on the way down. Okay, last example here for our modeling today, and we'll do some more tomorrow. On Monday with some practice when I'm there. So the value of John's stock portfolio is given by the function. Okay, let me go back. And notice this is in the incorrect order, so I'm going to put it in the correct order. 3t squared plus 77t plus 50. So 3t squared. So this one changes a little bit. And that's because this is a stock portfolio, right? So it's not talking anymore about a projectile. It's not throwing something into the air. Okay, 77x plus 50. All right, so now zoom out here. Okay, so this one's an upside down portfolio or parabola. So how much money did John start with? Okay, remember, always look for the y-intercept for that number. And he started with $50. What is the minimum value of John's portfolio? Well, you would say that it'd be something over here and say that this is a minimum value, but the problem with that is that this is a negative time, right? And he only starts with $50 because in a stock portfolio after that, it depends on where it goes. Well, if he started with 50, okay, and you can't go negative in time, then the minimum value in this case would be the same value. Okay, now if there's a min on the right side, then you would use that. But as you can see, a parabola just goes up and continues on forever. So then it says, well, after how many months will John's stock portfolio be worth $500? So this is, again, a situation where they want to know, where does it touch 500? So we type that in. I'm going to zoom in. And it reaches it after, let's see, it says time here is in months. So the time here would be 4.9 months, or about 5 months. That's very quickly if you think about it. His stock portfolio went from $50 all the way up to $500 in 5 months. Wow, that's impressive. All right, so that's how you work through the problems. You graph them in Desmos. This is all modeling. Okay, so your projectile motion. This is important to understand because we're going to do a rocket project at the end of the year, and this is the exact formula that we're going to use. Okay, so again, your assignment today, once you finish this, okay, work on quiz corrections. You will not have to turn them in, but obviously this is going to help you for Tuesday's quiz, and finish up missing assignments. Okay? All right, guys, you have a great weekend, and I will see you all Monday.